Okay, we're gonna go off to chapter 14 here, and so we should now be on to exam 4 material, I think. So this should be start of exam 4. We'll hit 11. We'll come back to 11 a little bit after we do a couple of these chapters, I think. All right, so we're gonna talk about liquids and solids, mainly liquids in this chapter. So let's talk a little bit about water. Water is colorless, tasteless. Water's normal sort of freezing point is 0 degrees Celsius. Its normal boiling point is 100 degrees Celsius. And anywhere between 0 and 100 degrees Celsius, we do have liquid water. Remember, as we talked about in the specific heat capacity, our specific heat sort of chapter, water has a relatively high specific heat, liquid water, about 4.184 joules per gram per degree Celsius, or 1 calorie per gram per degree Celsius. Water freezes, it does expand. The density of water typically, in most cases that you use it, is 1 gram per milliliter. Density does change with temperatures, so as the temperature changes, so does the density value. But as I think we might have talked about previously, pretty much if you do need a density sort of value, that 1 gram per milliliter is definitely the value that you would use. Now, the density of ice is 0.917 grams per milliliter. And water is an unusual substance, as very few substances in their sort of solid state are actually less dense than in their liquid state. And again, what happens is as water molecules basically come together in their solid state and they lose sort of energy because water is polar, when they start to sort of hydrogen bond with each other, which is how they sort of interact with one another, what ends up happening is it creates a lot of these really big open spots between the different water molecules. So they really can't get in there as tight to one another as normally can happen in the solid state. And because of that, we actually get a smaller density if we just think about sort of the density formula, which is mass divided by volume. So with all this open space kind of between the water molecules as they go into the solid state, it's kind of bloating the ice crystals, and their volume gets larger and their density will get smaller in that particular case. This is a heating and cooling curve, and this heating and cooling curve describes sort of what's happening with something, say, like water, as we go from different states. And as we sort of transition from one state to the next, there is a certain amount of energy that's required to do nothing more than sort of take something from one state to the next. So let's talk about that. We'll come back to the picture here. Um, and that is the heat of fusion. And the heat of fusion for ice, for example, is 6.02 kilojoules per mole. This is sometimes abbreviated as the delta H of fusion. And that delta H is that enthalpy sort of value we saw when we talked about energy. And the heat of fusion is really the energy to take something from solid to liquid, or liquid back to solid. And for the case of water, that's 6.02 kilojoules per mole, which roughly, for example, works out to about 300 and we'll call it 35 joules per gram, give or take. And for water, when we go from liquid to gas or gas to liquid for any substance, that's what's known as the delta H of vaporization. And for Water is 40.6 kilojoules per mole, which roughly works out to about 2,260 joules per gram for water as a transition. Now, when we talk about this happening as we transition from solid to liquid or liquid to solid, it actually occurs at the same temperature. Um, and that is the energy to do nothing more than change the actual state of a substance. It is not changing the temperature. So, because this happens at the same temperature, which in the case of water, for example, at 0 degrees Celsius and 100 degrees Celsius there, we would be going in an endothermic process. So it'd be like positive 335 joules per gram. Going from liquid to solid is an exothermic process, which means energy needs to be released. That would be minus 335 joules per gram. And it's really the same number. Again, just remember that typically speaking, right, anything that's a positive energy value basically means endothermic. Anything that's a negative energy type of value is exothermic. And the same thing would happen for our heat of vaporization. As you go from liquid to gas, that's an endothermic process. It would be positive, like 2260 joules per gram. Going in the opposite direction at 100 degrees, it would be minus 2260 joules per gram. So again, really the same number. The only difference is the sign, which indicates either it's going to be exothermic process or an endothermic process. Any questions on that? Now, these values that we see here, the 6.02, the 40.6, the 2260, and 335 is specific for water. If you're talking about some other substance, you would have different values for the heat of fusion and different values for the heat of vaporization. You would also have perhaps different boiling points and freezing points as well if it's a different substance than water, but water is kind of the common one that you come across. But again, if you're not dealing with water, you'll have some different values depending on the substance that you're dealing with. Now, if we look at this graph here, actually, I guess I gotta go this way too. We'll look at this one first, I think. So as I mentioned before, this is ice, which is basically the solid state. This is basically liquid water, which is obviously liquid, and that is steam, which is the gas version there of water. And as we can see here, this right here is 0 degrees Celsius. That is the transition between solid and liquid, once again happening at the same temperature. That is where we would apply our delta H of fusion. Depending on which direction we go, be the same number, just a different sign. Up here at 100 degrees Celsius, that is where we have the transition from liquid to gas, and that's where we would use our delta H of vaporization. Those are plateau lines, which means the temperature is not changing, but the state of the substance is changing. So again, that's where we would use either our fusion or vaporization. Now, if we look at this graph, we have some other sort of segments along the way. And in these segments here, this is the temperature changing, but everything there is basically in the solid state. This also is the temperature changing all the way through here, but everything here is also in the same state. And up here, once we get past it into the gas state, those are also the temperature changing, but everybody's in the same state, which is gas. And we learned about how to do those calculations, which is when we are changing the temperature, but the state of the substance stays the same. It says liquid all the way through, or gas all the way through, or solid all the way through. That is our friend from the past specific heat equation. Q equals delta S delta T, right? That is our heat, right, which is joules or calories. That is our mass, which is grams. That's our specific heat capacity. which is joules per gram per degree Celsius, our calories per gram per degree Celsius, and our change in temperature, which is our final minus our initial temperature. And remember, this is one of the few chemistry sort of equations that we actually do leave in degrees Celsius because our specific heat capacity is in degrees Celsius. That is also, if you remember, want to make sure that you do final minus initial temperature because that is the only place where you will get a negative, right? Is the difference in the temperature. So you always want to, again, make sure, as we did in that previous chapter, which I think was 10, if I'm not mistaken, we will do our final minus initial temperature here. So if you have any type of transition that's happening in this green area, where once again, we're staying in the same state, but changing the temperature, you would calculate the heat associated with that through the specific heat equation like we did previously. Anywhere where you are changing the state of a substance, but really not the temperature, which is those guys in the boxes there, that is where you would use something like the heat of fusion and heat vaporization. You could use this to figure out, if you took, say, ice from -2 degrees all the way up to steam at 105 degrees, you can figure out how much energy is required to do that entire process. And you basically just do it in parts, each part, figure out how much energy is required to do each of the parts. And then you could add them all together at the end there and figure out the total amount of energy is required to do so. Any questions on that there? So let's take a look at one, for example, and talk about this. So we want to know how much energy is required to change ice at, and that should be negative, I think, 3.5 degrees Celsius. Negative's hanging out up here. So that's negative 3.5 degrees Celsius to steam at 102 degrees Celsius. Now, let's take a look at this sort of graph. So really, the very first thing is we're going to be starting here. And that's basically ice, say, at -3 degrees. And the first thing that would happen is we need to take it from ice at -3.5 degrees to basically ice at 0 degrees Celsius. So that would be really the first thing that we would want to do. And in this case, we want to go from ice at -3.5 degrees Celsius to ice at 0 degrees Celsius. That is basically the same state all the way through, but we are changing the temperature. So this would be a specific heat calculation. Q is equal to ms delta T. Now, our mass here, we should probably know how much it is, how much energy is required to change. We'll just go with, only do 75 grams. That would probably be a good piece of information, I suppose, to know. 75 grams of ice from -3.5 to 102. So we do have our mass here, which is going to be 75 grams. We do need the specific heat capacity, but a reminder that we would not, in this case, want to use the 4.184 number because that 4.184 number is actually for liquid water. And this is water in the solid state. So you would want to look up the specific heat capacity for ice. And it's about 2, actually, joules per gram per degree Celsius. And we'll use that number. So you do want to make sure that you look up the right number. And it's somewhere in the ballpark of 2-ish joules per gram per degree Celsius. Our final temperature in this case is 0 degrees Celsius. Our initial temperature is -3.5 degrees Celsius. So we'll put our numbers in here. And that's going to give us Q is equal to 75 grams. Again, we're going to use our specific heat capacity for ice, which is about 2. And we're going to take our final temperature, which is 0, minus our initial, which is 3.5. And that's going to give us here about 525 joules of energy here. Now, that is just really the first step of this process. And that takes us to, if we kind of look at the picture here, it takes us to right about here. At this point, we're sitting at 0 degrees Celsius. We need to take it from ice at 0 degrees Celsius to liquid water at 0 degrees Celsius. So we have to do that phase change here. So we have to do the phase change, which would be our second step. And again, just really taking it, not changing the temperature, but taking it from 0 degrees Celsius ice and changing that water now into liquid water at 0 degrees Celsius. So the second step here would be to take ice at 0 degrees Celsius, write that right, 0 degrees Celsius, to liquid water at 0 degrees Celsius. That's our phase change. And again, with a phase change, that is where we're going to use our heat of fusion here. And for water specifically, it's roughly 335 joules per gram, which is what we're going to use. That's that 6.02 kilojoules per mole number as well. So we're going to take our 75 grams of water at this point. We're going to times it by the heat of fusion. And that's going to give us 75 times 335, about 25, 125. So this energy here, 25,125 joules, is the energy to do nothing more than to change the phase, right, of that guy from solid to liquid. Any questions on that so far? Yeah. It's sort of a constant value. That's the heat of fusion for water in joules per gram. Is the conversion of the 6.02 kilojoules per mole number. So it's kind of conversion. And again, that is once again specific for water, that heat of fusion is specific for water. Other questions? All right, so if we look at our sort of map where we're at, we're now sitting, since we just did the phase transition, we're sitting here at 0 degrees Celsius liquid water. Really, the next part of the transition is to take it from 0 degrees Celsius all the way up to 100 degrees Celsius liquid water. So that is a transition where we're going basically changing the temperature. It's going to be liquid water all the way through the little red line that I drew there. So that is where we're going to use our specific heat capacity to do that. Again, same phase temperature changes. So we're going to go from 0 degrees liquid water to 100 degrees liquid water. And we'll use our specific heat equation. Q is equal to ms delta T. Here, our mass is still the same. At this point, though, we are now into liquid water, which means we do want to use the specific heat capacity we're familiar with, which is that 4.184 number. Our final temperature here would be 100 degrees minus 0 degrees. And that's going to get us here 75 times 4.184 times 100. That's going to get us here 31,380 here. Any questions on that so far? All right, so now that we've heated up the liquid water from 0 to 100 degrees, if we look at our little diagram here, really the next thing that we need to do is another transition. And we're sitting here at 100 degrees liquid water. We now need to take it at 100 degrees to 100 degrees gas, basically. So we need to do a transition from liquid to gas at this point. And that is going to be our heat of vaporization. Again, that's going to happen at the same temperature, but the only thing we're going to do is change the phase of it. So that is what we would do next, which is do our transition 100 degrees liquid water to 100 degrees water in the gas phase. And that is our phase change. We're going to use our delta H of vaporization, which again, I'm going to use the joule number since we're doing all these in joules. That's the 2260 joules per gram. Once again, it's that 40.6 kilojoules per mole number for liquid water. So we'll take our 75 grams. We'll use our 2260 joules per gram. And to do the phase change there, 75 times 2260 gets us about 169,500 joules to do that phase change. Any questions on that calculation? By the way, looking at both the numbers and just looking at the different transitions here, which one requires more energy to do? The transition between solid to liquid or transition from liquid to gas? The one from liquid to gas takes a lot more energy. As you go from solid to liquid, everybody's still relatively close to one another. But as you go from liquid to gas, you got to get everybody broken apart from one another. So it takes a lot more energy to get everybody completely apart from another. And that's what we see if we just look at the difference between the two phase changes, 25,000 for the solid to liquid, about 169,000 to do it from liquid to gas. What's that? You again should know specific heat of water. Like before, I would say they probably will pop up. I can't promise you as you continue on in your career if they will pop up or not, so you might want to kind of put those into your memory. But the per us will probably pop up, but still you need to know that specific heat of water and stuff like that, like you had to know previously. Other questions? All right, so we're almost there though. We're now sitting, if we look at our little diagram, at that last dot, which is 100 degrees Celsius. We actually have one more little spot to go, which is we actually want to end at, I think it was 102 degrees Celsius. So the last step that we want to do is take it from 100 degrees Celsius gas to 102 degrees Celsius, which is our fifth sort of step there. And in this case, I'll do it here maybe. Fifth step would be 100 degrees gas to 102 degrees gas. And again, here we're in the same state, just changing the temperature. So we're going to go back to our specific heat. And we're going to put in our 75 grams. We are at the gas state of water, which also has a different specific heat capacity. And I'm just guessing, but I'm going to go with 2.03 joules per gram per degree Celsius. I can never remember. Either the ice is that or the gas one's that, but I think I might have guessed right, hopefully. We'll see. But they're pretty close to each other. So once again, we do not want to use the 4.184 version. Here, our final temperature, 102 minus 100 degrees Celsius. And it's about 304.5 joules. So that is the energy again, just to take it that last little step. Now, if we want to know the total energy here, the total energy would be the energy from step 1 plus the energy from step 2 plus the energy from step 3 plus the energy from step 4 and the energy there from step 5. So what we do now is just kind of go back and add up all those. So we'll take our 525 plus our 125 plus our 380 plus our 500 plus our last step here, which was 304.5. That's going to give us something in the edge of 22,685 joules. Or if we're going to look at kilojoules, about 227 kilojoules of energy is needed to do that. Any question on any of those? steps there. Now, we ended up with obviously a positive value, right? So as we're going in this direction, which is a heating curve, it is endothermic, which is what we would expect. What would be the difference if we started at 102 and went to minus 3.5 degrees Celsius? What would be the only difference? Yeah, everybody would be negative, and we would end up with the same number, just be negative. If we were going in this direction, we would end up with negative, as it would be exothermic. And really the only difference in your calculation is, for example, these guys would switch, which would give you a negative. This would be negative if you're going the other direction. Once again, these guys would switch, which would give you a negative. This guy would be a negative. And lastly, obviously, these guys would switch, and that would give you a negative. So you would end up with negative values all the way through. Again, the numbers would be pretty much the same all the way through there. Any questions on that? So sometimes if you come across a problem like this, it's kind of helpful to think about a little graph like this. That way you don't miss any of the steps along the way that you need to do. Pretty much if you sort of have this graph or make this graph anywhere on the graph where it's a flat line-ish, if I drew it flat there, that is a phase transition, which means, again, it should be like your delta H of fusion, your delta H of vaporization. Anywhere where you are kind of going upwards on the graph, which would be obviously here, here, and here, that is a specific heat equation and calculation like we've done previously. So anywhere, once again, temperature changes, state stays the same, specific heat. Anywhere temperature stays the same and the state changes, delta H of something along the way. Any questions on any of that? And obviously, that's like we did here. If you want the total amount of energy, just add up all the parts, basically. Yeah. Questions? Okay. All right. So the next thing we're going to talk about are forces that hold molecules together, and also forces that molecules use to interact with one another. The first thing we're going to talk about is an intramolecular force. An intramolecular force are the forces that hold basically an atom or molecule basically together. So for example, if you think about one water molecule, this one water molecule is held together by covalent bonding, which is sharing of electrons. And those are the intramolecular force. We also have, for example, ions, right, that are held together in a solid sort of situation. These are held together by electrostatic attraction. That is also an intramolecular force. It's the force that basically holds that guy together. Intramolecular forces, which is like ionic bonding, covalent bonding, always much stronger than intermolecular forces, which are the forces that hold two different molecules together. So intra means within the molecule. Intermolecular forces means the forces that hold one entire molecule together with another. So for example, if we had two different water molecules, and water, as we've talked about, is polar, so they're going to be attracted opposites here. And that is an intermolecular force. And that's the force that holds this entire water molecule together with this other entire water molecule. And once again, intramolecular forces would be the actual bonds in one water molecule between an oxygen and hydrogen, would be the intramolecular force. Now, intermolecular forces are always much weaker than any intramolecular force. And that is because if it was the opposite, we would have trouble when we do things. And we know, just in logically speaking, it is not the opposite. So when we heat something like water, as we've done many times, it actually starts to boil, and boil makes steam, and steam is still water molecules just in the gas phase. That means as we heat it, the first bond that breaks is actually the bond between the different water molecules. And once again, that allows this water molecule to go into the gas phase, as well as, for example, this water molecule to go into the gas phase. Once again, we know the intramolecular forces do not break apart, because if they broke apart first, then we would be breaking these bonds, which means we would be making hydrogen gas and oxygen gas. And that doesn't happen when you like boil water again to make dinner or something like that. That would not be so good. You would have barking and all that kind of stuff happening as you would make that gas. So intermolecular forces are always much weaker than any intramolecular force you come across. And once again, intramolecular forces within one single molecule, what holds it together, basically covalent bonding, ionic bonding, that's happening there. So what are intermolecular forces, and what are they basically, or how they basically work? It's a very simple interaction that pretty much all intermolecular forces is the very simple idea that the negative side of one molecule is attracted to the positive side of the other. So pretty much all intermolecular forces is pretty much that's what they're looking for. That's how they interact with each other. Negative side of one attracted to the positive side of another. Intermolecular forces are also really important in terms of things like boiling points, melting points, freezing points. So they affect things like melting points, freezing points, boiling points. And the stronger the intermolecular force, the higher we have for these things. So the stronger the intermolecular force, the higher boiling points, melting points that we typically have. The weaker the intermolecular force, the lower the boiling point. And that makes sense if you just think about it with, say, this example here. If this was a really weak interaction, you wouldn't take a lot of energy to get those guys to break apart, and we would translate to a much lower boiling point. If this is a really strong intermolecular force, it's going to take a lot more energy to try to break those guys apart. And the result of that is we would have a higher boiling point, for example, in this case. That's why, for example, as we'll talk about, things that are nonpolar, say like methane, propane, butane, they are held together by super weak intermolecular forces, and it doesn't take a lot for them to go in the gas phase, which is why they're usually found in the gas phase, because they're basically held together by not very much of a force. So we're going to talk mainly here about intermolecular forces and the different types of intermolecular forces there are. The first type of intermolecular force is a dipole-dipole interaction. Now, you might remember dipoles from when we talked about bonding. Dipoles is a result of a dipole moment happening, right, which is illustrated with this arrow. And if something has a dipole moment, it is a polar molecule. And really what that means is it is always, no matter what the situation going to be, it has a negative side of the molecule and it has a positive side of the molecule because of the unequal sharing of electrons. So because it's polar, it will always have that type of distribution. And dipole-dipole interaction is when we have dipole moments. And essentially what happens is you have pretty much one that has a positive negative side. And when it interacts with another polar molecule, either another one like itself or a different molecule altogether, they will align themselves in a way that the positive side of one be attracted to the negative side of the other, and that is how they're going to interact with each other. This is the main type of interaction that occurs for polar molecules and polar molecules. This is basically how they interact with each other. And these are polar molecules, and I'll write this now, that typically cannot hydrogen bond. And again, we'll talk a little bit about hydrogen bonding in just a second. But pretty much if you have a polar molecule and it doesn't really have the ability to hydrogen bond, it will pretty much be using dipole-dipole interaction as its main interaction for how they will interact with itself and, again, other polar molecules in this case. It's only about 1% as strong as covalent ionic bonds. And once again, that is because covalent and ionic bonds are intramolecular forces, which, as we just talked about, are much, much stronger than that. So here we go, maybe.
Bonds between atoms with different electronegativity have a permanent dipole, that is, a separation of charges, because of the unequal sharing of electrons. Some molecules which contain polar bonds do not have a net dipole. For example, carbon tetrachloride has polar carbon-chloride bonds, but the polarities cancel as a result of its symmetrical structure. It is therefore a nonpolar molecule. Even though the chloroform molecule has a tetrahedral shape, one of the outer atoms is different from the others, so the molecule is not symmetrical. This means the bond dipoles do not cancel, and the molecule has an overall dipole moment. It is polar. Molecules such as sulfur dioxide have asymmetrical structures due to one or more unshared pairs of electrons on the central atom. Sulfur dioxide is an asymmetrical molecule with polar bonds. Therefore, it is a polar molecule. When polar molecules, such as sulfur dioxide, are close to one another, they tend to align so that the positive end of one molecule points towards the negative end of another molecule. Attractions among polar molecules are called dipole-dipole forces.
So as we saw there in the little animation, when these polar molecules come together, they really do try to align themselves to really maximize the attractive forces that occur and minimize the repulsion forces that occur. No matter what you do, for example, say in liquid state, you're always going to get some negatives near negatives and positives near positive sides of molecules, which they really don't want to be. So what they'll do is they'll kind of keep moving around so they can find sort of a arrangement that's sort of okay for them, energy wise, to sort of again maximize that attractive forces. So as you can see here, we're trying to maximize those attractive forces and again minimize areas where we have the same sort of charge near each other. So they'll move around a little bit, kind of wiggle around a little bit until they do that. A reminder here that again, we are talking about molecular polarity. So we're not just talking about something that has polar bonds. We're talking about whether or not the entire molecule is polar or non-polar. Remember, as they showed in that example, if you had I think this is what they had there. Although it does have polar bonds, right? This is one of those symmetrical geometries, which means although it does have polar bonds overall, this molecule is going to be non-polar. And what non-polar basically means is we have equal sharing of electrons. And when you have something like that, it essentially is like neutral. There is like no charge. There's no side that's more positive. There's no side that's more negative. Like they did when they swapped out one of the fluorines there for hydrogen. Now what you have is a polar molecule overall, where towards the fluorine side is going to be more negative, towards the hydrogen side here is going to be more positive in this case, and this will create a kind of separation of charge where it can use dipole-dipole interaction. Any questions on that there? As also with SO2 as well. So remember that essentially, if you're looking at something and you want to determine is this a polar molecule or not, you want to think about symmetrical, unsymmetrical geometries like we did when we did bonding. And again, if it's an unsymmetrical geometry, it's got dots on the central atom, it's probably going to be polar. If it's a symmetrical geometry with no dots on the central atom, all the outside ones need to be the same for it to be non-polar. And if all the outside atoms are not the same, then it will be polar most likely. So remember the quick way to determine is this a polar molecule or not? Now, hydrogen bonding is a special really type of dipole-dipole interaction. It's really a part of dipole-dipole, but it's a much stronger sort of interaction. And with hydrogen bonding, it happens when we have a hydrogen that is directly bound to either nitrogen, oxygen, or fluorine. And if you look at the periodic table, that is the upper right of the periodic table, and that is our most electronegative element is fluorine, right? So when you have hydrogen bound to either nitrogen, oxygen, or fluorine, you're going to have a big sort of separation in electronegativity values, and you will create these polar bonds that will occur. And the presence of these polar bonds are going to allow it to do what is known as hydrogen bonding. And that is what we see with water. Water, once again, we have a hydrogen that is bound directly to an oxygen. Once again, negative, positive. So again, we're going to get some hydrogen bonding happening here. This is probably one of the strongest intermolecular forces you could have. So earlier we were talking about intermolecular forces can affect things like melting point, boiling point. If you have somebody that has the ability to hydrogen bond, you're probably going to have a pretty high boiling point and melting point because of that. That's pretty much one of the strongest sort of intermolecular forces you could have, is something that has the ability to hydrogen bond. This is what I was talking about earlier. Now, if we have a polar molecule like we just saw there, like this guy, can this guy hydrogen bond? This guy cannot hydrogen bond. Can this guy hydrogen bond? This guy cannot hydrogen bond either. Again, you need more than just a hydrogen to be present for it to hydrogen bond. The hydrogen needs to be directly attached to a nitrogen, oxygen, or fluorine, which is what we see here, right? Hydrogen directly attached to that oxygen. This is actually a non-polar bond, right? And so this guy, though, is a polar molecule, and this guy would use dipole-dipole. This guy will use hydrogen bonding. So this is an example, as I was talking about earlier, of a polar molecule that doesn't have the ability to hydrogen bond. It would only use dipole-dipole as its interaction. It cannot use hydrogen bonding because it doesn't have the ability to do so. And that, again, is a common mistake that people make, is they see a hydrogen and go, oh, it kind of makes sense. It has a hydrogen, it should be able to hydrogen bond, but it does need to be bound directly to one of those three elements in order for a hydrogen bond to occur. This guy's got a load of hydrogens, all nonpolar. This molecule itself is actually nonpolar. It can't do either of those. It can't hydrogen bond. It can't dipole. I'm going to talk about what it will do in a second, but it won't do either of these things. So again, just the presence of those hydrogens doesn't mean that it can't hydrogen bond. Any questions on that there?
Some polar molecules have unusually strong intermolecular attractions called hydrogen bonding. These attractions occur in molecules where hydrogen is bonded to fluorine, oxygen, or nitrogen. The interaction occurs between the hydrogen of one molecule and an unshared electron pair on the more electronegative element in another molecule. The orientation of hydrogen fluoride and water molecules in the liquid states of these substances is determined by hydrogen bonding. The hydrogen atom in hydrogen fluoride is attracted to the fluorine atom on another hydrogen fluoride molecule. Water with two hydrogen atoms and two unshared pairs of electrons can form 4 hydrogen bonds per molecule. In ice, hydrogen bonding leads to a tetrahedral arrangement of water molecules around one another, forming 6 membered rings that leave open channels through the ice structure. In liquid water, the tetrahedral arrangement is not fixed because the molecules are able to move around, and on average, a water molecule is surrounded by 3.4 other water molecules. Hydrogen bonding forces are unusually strong attractions that occur among molecules in which hydrogen is bonded to a highly electronegative atom.
So as you saw in that little video there, we saw the ice and sort of liquid water example. We talked about density. As you saw with the ice part there, because it doesn't have as much energy when they do come together, hydrogen bonding creates all those big open spaces between the water molecules. When they're in the liquid state, they have a little bit more energy, so they are able to kind of move around a little bit more, so they don't get all those big openings between the water molecules, as we talked about there with ice and as you saw in that little animation. Any questions on that there? So here again is an example of our hydrogen bonding, negative side of one and positive side of the other in this particular case. Now, the next type of interaction is what is referred to as dispersion forces. Dispersion forces, also sometimes referred to as London dispersion forces, are really the main intermolecular forces for our friends, which are pretty much nonpolar molecules. So this is pretty much how nonpolar molecules interact with themselves and other nonpolar molecules is through dispersion forces. Dispersion forces are frankly the weakest type of interaction that you could have. It has to rely upon something happening temporarily to give it a charge. So the deal is this: temporarily here, or normally, if we have nonpolar molecules like these two, there is no separation of charge. It's pretty much a neutral guy. There's a couple of things that could occur to temporarily give these guys this interaction. We could have something come up on it like an ion that has a charge, a positive or negative charge. Positive or negative charge. Or we could have a polar molecule temporarily come up on it. And for example, if we had a nonpolar molecule here and we had an ion, for example, a positive ion come up on it, or a polar molecule come up on a nonpolar guy. Temporarily, what that's going to create in our nonpolar molecule is the electrons in here are going to be attracted towards the positive ion. And same thing here, electrons would be attracted towards the positive side. And temporarily, what that will do is create a separation of charge in our nonpolar molecule in each of these cases. And now they have a way to interact with each other. Problem is, as soon as that ion or molecule moves away, there goes the separation of charge in the polar guy, and they're going to revert back to basically having no charge. That's why it's temporary, right? That's why when you put like water, which is polar, and like oil, right? It will kind of mix for a little bit and then it will kind of separate out. It can't maintain that interaction because it doesn't have a fixed sort of positive and negative charge. The other thing that can happen is in these nonpolar situations is if you have a couple of nonpolar molecules, all the electrons, for example, in this particular molecule may decide, hey, let's just, kind of vacation over here. And if it does, what it's going to temporarily do in that first nonpolar molecule is create a separation of charge that's going to temporarily occur. And that's going to cause the electrons in this guy to go, cool, I'm kind of attracted. So now we're going to get two of these guys that normally do not have charges will now temporarily have a charge and they're able to interact with each other. This is what is known as polarizability. It's the ability at which those electrons can just randomly, because they're flying around, just all end up on one side of the molecule versus the other. These are temporary because eventually those electrons are on the move, which means they're going to kind of go back and it's going to lose its separation of charge. It's going to these ones. So these are super weak sort of interactions, dispersion forces, because it depends on something happening for them to basically be able to interact with one another. Now, the strength, though, of dispersion forces, so the strength of dispersion forces, if you're looking at, say, two things that have dispersion forces and use dispersion forces as their main intermolecular forces, increases with increased molar mass. And the reason for that is if you increase molar mass, that probably means that you have more atoms. And if you have more atoms, that means you have more electrons. And if you have more electrons, you have a greater opportunity for those electrons to go one way or the other and sort of separate out a charge. It also gives more places where that interaction could actually occur. So if you're trying to determine the strength of a dispersion force versus another dispersion force, the one that has the greater molar mass will be the stronger dispersion force. Still super weak, but it'll be the strongest, weakest force, if you will, in that particular case. That means if you're comparing something like CH4 to something like C10H22, the C10H22 has a lot more atoms, a lot more electrons, will have a higher boiling point than CH4 that has less atoms, less electrons, and so forth. So they both will be using dispersion forces, but the one with the higher molar mass will be a higher, stronger dispersion force. That brings us to our guy, methane. Methane is a nonpolar molecule, and it's going to use dispersion forces. So that is what that will use. So pretty much a lot of organic guys, which are nonpolar molecules, this is pretty much what they use, which is dispersion forces. And that's why a lot of organic things like propane, methane, butane, we think of them as gases because they are held together by super weak sort of question on that there. This, by the way, is what is sometimes referred to as ion-induced dipole, because you're using an ion to temporarily give this other guy a separation of charge. This is what is sometimes referred to as a dipole-induced dipole. Any questions on that there?
Solid carbon dioxide, dry ice. Nonpolar molecules are arranged close to one another in a regular array where they move slightly around an average position. The distribution of electrons in a molecule can occasionally become asymmetrical, leading to the formation of a temporary separation of charges, a dipole. Partial changes on the molecule that form a temporary dipole then influence the electron clouds of nearby molecules. Although the dipoles are temporary, there is a significant attractive force between adjacent molecules as a result of the deformation of their electron clouds. These attractive forces are called London dispersion forces. London dispersion forces are the only type of intermolecular force found in nonpolar molecules.
So this is what we were talking about, sort of an instantaneous dipole, which is what the little animation also showed. Again, normally they do not have a dipole moment. They do not have a separation of charge, but temporary, because of the electrons sort of going one way or the other, they will temporarily gain those charges, partially positive, partially negative, and again have a way to interact with one another. Now, when we talk about these sort of forces, let's talk about a couple of things. We have our hydrogen bonding, which is the strongest intermolecular force. And again, this is pretty much the main interaction that a polar molecule that can hydrogen bond will have. And again, like we saw with water, by the way, if we had something like this, like methanol, Although methanol does have a nonpolar part, which is here, it does have this little part right here, which is a hydrogen directly attached to an oxygen, which means it does have the ability to hydrogen bond through that spot right there. So it is possible to have a molecule, and a lot of organic molecules, for example, have a side that's kind of nonpolar, but it will have this like little group that is polar and gives it the ability, for example, to hydrogen bond as well. So something like that also affects the solubility, as we'll talk about in the next chapter. So something like methanol there on the bottom, because it has that OH group, will also be able to interact well with water. And that is why they will be soluble in each other because of that interaction that they're able to do. Dipole-dipole is also really a strong intermolecular force. It is those polar molecules that do not hydrogen bond. So these are the guys who's able to do that. So we saw our SO2, right? It's able to do that and basically interact with another one. So once again, that is our positive, negative, negative, positive interaction that's happening there. With our sulfur in this case being more positive, oxygen side being more negative in the case of SO2. The weakest of all of them are dispersion forces. And those are pretty much your main source for our nonpolar molecules. And that's, something that is definitely like this. We also saw CO2 as an example of that there. This is pretty much the force that they're going to use. To be honest with you, everybody can use dispersion forces, even polar molecules. That is also why, they're kind of interact for a short period of time with something that is sort of non-polar. But the main route for polar molecules that have the hydrogen bonding is to be able to hydrogen bond will be that hydrogen bonding, which is the strongest. This is the weakest out of all of those. So anything that's using dispersion forces will have probably a lower boiling point, melting point, then something here that's using hydrogen bonding will have a higher boiling point, melting point situation. Any questions on that there? So why is dispersion forces weak compared to, say, dipole-dipole and hydrogen bonding when they all use the same type of interaction, which is a positive-negative interaction? The reason it is because when you think about anybody that can hydrogen bond or anybody that can do dipole-dipole interaction, they have a dipole moment, which means no matter what you do, for example, to water, you do whatever you like to water, it always has a positive side, negative side, which means it's good to go. It's ready to bond. It's never going to kind of change that. It's ready to do that interaction. And that's different than a nonpolar molecule that relies upon dispersion forces. It pretty much has no charge. It needs something to happen for it to get that charge. And because it only can get that charge through a couple of ways, it has to rely upon that, and that charge is only going to be temporary and is going to break apart, which means it has no way to maintain that interaction. And that is also why, again, things that are polar and things that are non-polar are not soluble in each other, because one is using somewhere where it's always good to go. The other one's not really good to go. It needs things to happen, and they have no way to maintain their interaction with one another over a long period of time. And that's why non-polar and polar things not very soluble. That's also why, as we'll talk about in the next chapter, polar and polar things are really soluble in each other because they're both coming to the table ready to bind. They're both got the positive negative side. They're ready to interact really well with one another. By the way, though, non-polar, as we'll talk about, and non-polar guys also going to be really soluble in each other, because even though they're using very weak interactions, they're using the same type of weak interaction. So they're able to really mix really well with each other because they both have that temporary sort of attraction force that can happen. Any questions on any type of intermolecular forces? Another type of intermolecular force that sometimes falls in here with dipole-dipole is something that we do a lot when we dissolve like an ionic compound in something like water, right? So when we dissolve something like a positive ion in water, water will surround it with its negative side, right? And there'll be that attraction between the negative side of water and that ion that you're dissolving. And that's how something dissolves, as we talked about. It gets kind of trapped in the water network and matrix. This is what is sometimes referred to as ion-dipole interaction. And that's basically the interaction that we use when we dissolve any type of ionic compound in something like water. Basically, the negative side of water attracted to the positive ion, while the positive side of water, which is the hydrogen, is attracted to the negative ion there. So that's another sort of interaction that we use a lot when you dissolve some type of ionic compound in a molecule like water, sometimes referred to as ion-dipole interaction. Any questions on any of the interactions there? All right. So do that. So we talked a little bit about a couple of things here, but let's talk about vaporization and evaporation. Can occur when a molecule in a liquid can escape the liquid surface to form a gas. And it requires a lot of energy to overcome these intermolecular forces. So as we talked about with vaporization, that process as you go from liquid to gas, that happens again at the boiling point. All right, so that's at the boiling point of a solution. And if it is held together by a strong intermolecular force, you're going to have a much higher boiling point than if it's held together by a weaker force. So once again, the force that holds this molecule together with this molecule, if that intermolecular force is really strong, high boiling point, and if it's kind of weak, a lower boiling point. The opposite process is what's known as condensation, and that's when gas molecules basically lose some energy and they kind of drop back off into the surface or into the liquid part. At the surface of any liquid, you have that process happening. You have guys that have enough energy to escape the liquid and go into the gas phase. And then you have some slower moving guys that will drop back down into the liquid phase, right? Um, when we talk about how much gas is above a liquid, because of this process, that is what is known as the vapor pressure of a liquid. So liquids with high vapor pressure are said to be volatile. Liquids that have high vapor pressure means that they typically will have very weak intermolecular forces. Volatile means they evaporate really quickly, which means if you have something in a liquid that's held together nonpolar like, you're going to have a lot of these guys just looking to jump out of the part of the solution, and you'll have a lot of gas molecules over the liquid, and that means you have a lot of vapor over it. And because you have a lot of gas molecules over the liquid, you have a much higher pressure, right? Because gas molecules, more pressure, and they will start to evaporate a lot quicker. If you have something that's held together by a really strong intermolecular force, you will probably have a much lower vapor pressure because it's going to take a lot longer and harder for those guys to try to escape the liquid part, and they're going to stay in the liquid, which means less of it will escape the liquid part, and you'll have less gas molecules above the liquid. The vapor pressure of a liquid at a given temperature is again determined by the intermolecular forces on it. This is also like the process of evaporation, right? When you have a little liquid on the bench or whatever, right? You got a good rate of evaporation that occurs. You also have condensation coming back. The problem is when you have a little bit of liquid, there's air that blows those guys away. And when those guys get blown away, they're not going to drop back into the liquid. And eventually the little spot you have on your bench here will start to evaporate off, right? If you put that water into a beaker, it takes a lot longer for it to evaporate if it's open, right? And it will still do the same process, but there's a lot more molecules kind of underneath the surface there that got to get to the surface to escape. So it's going to take longer for it to evaporate. And also, right, if you don't want something to evaporate, you put a lid on it, right? Then it has no way to escape. It's got to stay in the actual container that it's in, right? Speaking of a solution in a container, when we put a solution in a container, the first thing that we will see is at the beginning a rate of evaporation. So we'll have this evaporation going. In this case, though, it has no escape route. So eventually we'll have some condensation coming back in, and eventually it'll reach equilibrium, which means that the rate of the evaporation will equal the rate of the condensation. And what you will actually notice if you look at it really carefully is the liquid level where you started with. And when it reaches that equilibrium, will actually be a little bit lower. And that's because when you first put the liquid in the container, you had no evaporation. And then evaporation started, right, which is going to lower your liquid part until it reaches equilibrium. And you'll actually end up a little lower. This is what is causing the vapor pressure, right? All those gas molecules above the liquid, right? Colliding and coming in contact with everybody. And that is basically the vapor pressure there, is that pressure of the gas that is over the liquid. Any questions on that there? All right, we're going to lay it up there, I think, for today.